he has some open problems on the topics of recurrence and special systems. Professor Furstenberg.
We learned this morning, somebody didn't know that you have a transformation of a compact space, there always exists recurrent points. Another point is recurrent, x is recurrent and here's the difference between ergodic theory and topological dynamics is that in ergodic theory the transformation is called T, and in topological dynamics the transformation is called F. But so I call it T. So if there exists a sequence NK going to infinity, the T to the NK of X goes to X. Now, since there always exists a recurrent point, I get recurrence for it. How small can I make a subset and still get recurrence? So let's define a sequence. Let's say that a set, let's say R, contained in the integer, in the natural numbers, is compact recurrent. C recurrent if for any T taking x to x compact, so x converging to x. So it's interesting, some interesting examples which are non-trivial. For example, the sequence ends, if I take a set of squares, this is compact recurrent. And that's a non-trivial statement that follows actually from an ergodic theorem for if you look at a unitary operator and look at n squared, so it's a non-trivial result, but it's an example which of something that's compact recurrent. So at any rate, this is one definition. Another definition, something less restrictive, is, let's say, S containing N is Bohr. Bohr for almost periodic functions is Bohr recurrent. If for any torus T T to the M equals Rn over Gn, and rotation, and the rotation of the torus, again I'm looking at a special space, and I'm looking at a special kind of transformation of the space, and say alpha belonging to the torus, to this torus, there exists nk in S, and x belonging to the torus with here not now because of the homogeneity. I don't have to really write this. So all I have to write is that nk alpha converges to 0 in T to the n. And that means that for any point, in fact, it'll come back to itself along nk times nk. So this is a very restricted type of recurrence, before I formulate the question, if you're not in a hurry, I'll tell you a little bit of the history of this. Erdős asked Katznelson a certain question about coloring a graph. In the graph, the question was, suppose I take Z as the vertices of the graph, and I want I'm not telling you what the edges are. These are the vertices, and let lambda be some subset of natural numbers, and what I want to know, when you say we have an edge, and n is an edge of this graph, if n minus m, or let's say absolute n minus m belongs to lambda. You join m to n if their difference depends on how many their difference. So basically, what you have is a translation invariant graph, since this depends only on the difference, and now you want to color this graph, and you want to know what the chromatic number of the graph. You can ask, what is the chromatic number of the graph? In other words, well, basically the issue is the chromatic number finite or infinite? Now, if it's infinite, that means that that I have to break it into small pieces in order to avoid some difference being inside lambda. Erdős's question was asked if lambda is lacunary, does this imply, so lambda is pretty small, that means you don't have that many vertices, that means you don't have that many connections.